What's up, everybody, and welcome back to another video from the Scalar Learning channel on ACT Math. This is part 2 of 4 for the critical concepts. Once you watch this entire series, you'll know everything you need to know for the ACT Math portion. Without further ado, let's do it. So first, we're going to talk about quadratic functions. We're going to talk about what they are, what to look for in terms of the critical pieces of information you need to be able to extract. So the graph of a quadratic function is what we call a parabola. It looks like a U, and it can either go up like this or it can go down like this. Now, these are both centered at the origin, meaning the vertex, that critical point where it kind of bottoms out. It's either the bottom or the top, the min or the max. That is the vertex, and this is centered at the origin 0, 0. And once again, it's called a parabola. When it comes to quadratic functions, there are 3 critical values. First, we have the y-intercept. And when you're talking in context of a word problem, or for example, where you're dropping a ball or this and that, it is your starting point. And remember, the x value is always going to be 0 at the y-intercept. So just remember, this is a starting point. You're trying to figure out at what value does whatever you're modeling begin at. Next, we've got the x-intercept, and the x-intercept is where, again, y is going to equal 0, and a lot of times we define this as the point of 0 value. So for example, if you're modeling the height of a ball being dropped, it's when it's going to hit the ground. It's when it's going to have a height of 0. If we're talking about revenue and profits, we're looking at a point where revenue or profits equals 0. Last but not least, we have the vertex, and the vertex is going to model either the max or min value of this function. So again, if we're talking about modeling revenue, the vertex would probably be the point at maximum revenue, maximum profit, whatever it is you're modeling. Again, if it's an upward facing parabola, you would find your minimum value point at the vertex. Now let's talk about standard form of a quadratic. It's simply ax squared plus bx plus c. And this is super important as we go on to remember this ax squared plus bx plus c format, because we can use that to find different components of a quadratic function. The defining characteristic of a quadratic is that the highest degree is going to be 2, meaning that x squared, you're not going to see any exponents above that, but you got to see that at least once. So now we're talking about standard form. Again, here's an example of a quadratic in standard form, where a is 2, b is 4, and c is -6. And there you are. Those are your a, b, and c values. And once again, we're talking about a parabola, and this is going to be an upward facing parabola. You know it's upward facing because that a value, the red value, is positive. The other interesting thing to note is when it's in standard form, you're getting the y-intercept in that c value. So you have a y-intercept of 0, -6. Now we're going to take the same quadratic function and present it in intercept form. Now, intercept form is where you basically see it in factored form. And what's cool about this format is you can clearly see the values of the x-intercept right in the function. So see what's in purple and orange, those are the intercept values. So I'm going to show you the graph. The only thing to remember is the intercepts are the opposite of what you see in the function. So there you see a +3. Well, that x-intercept is actually at -3, 0. And that -1 is actually a +1, 0 for the x-intercepts. Now we're going to take the same function and present it in vertex form. So vertex form is y equals a times x minus h squared plus k. And what's cool about this format is you can clearly see what the vertex of the function is. So in vertex form here, we have y equals 2 times x plus 1 squared minus 8. Again, it's been reformatted for you already. And notice in purple, you see a 1. And in orange, you see an 8, but it's really negative because of the minus there. So the vertex is h, k. Notice the purple and the orange values. And again, you see it's x minus h. So for the x value of the vertex, we're taking the opposite of whatever you see inside the parentheses. So the vertex is at -1, but -8 also. So for the y value, it is whatever it is in the equation. There's a minus there, so it's a -8. Now we're going to talk about finding the vertex when something is in standard form. So again, in vertex form, it's pretty easy to spot, but what about if it's presented in standard form? How do we do it? So here's our same function, and this is the key, right? If we know that it's in standard form, the vertex is at -b over 2a. And again, that's the x value of the vertex. But once you know the x value, you can plug it in to the function and find the corresponding y value. So in this case, our b value is 4, our a value is 2. So we're going to have -4, because it's a negative b value, over 2 times that a value of 2. And when we simplify it, we get negative 4 over 4, which is simply negative 1. And once again, as we saw before, this makes sense, right? Because we have a vertex at negative 1, comma, negative 8. Now let's talk about solving quadratic equations. And the method of choice is going to be factoring if it's possible. So when we talk about factoring, let's take an example of a quadratic equation. X squared plus 5x minus 6 equals 0. And by the way, it's very important for quadratics that when we're trying to solve them like this, we set everything equal to 0. I'm going to show you why in a second. So then we're going to factor this guy. So how do we factor? Well, we look at that green value and that blue value, the b and the c values. And so we say, what multiplies to the c value, in this case negative 6, and adds to the b value, which in this case is positive 5. So the two numbers, and you can kind of play around with numbers and combinations and such, but the two numbers that come to mind would be positive 6 and negative 1. So that's what goes in those parentheses. You see a positive 6 and a negative 1. If you multiply those two binomials together, you'll see that it goes back to the original equation, x squared plus 5x minus 6, as long as you remember to FOIL. We're going to talk about foiling in a second. But this is great because now you have two things multiplying each other to equal 0. And what's special about that is 0 times anything is 0. So all you have to do is figure out what value makes the left binomial go to 0 and what value makes the right binomial go to 0. So what plus 6 is 0? Well, that's negative 6. What minus 1 is 0? That's positive 1. So my two solutions to this equation are therefore negative 6 and 1. Now we're going to talk about using something called the star method, and this only comes into play when you've got a leading coefficient for a quadratic. And by leading coefficient, I mean that a value, that red value of 8. So this is not as easy to factor, but there's a really amazing method called the star method, which I'm going to show you how to do it right now. So first we create this cool little star-shaped thing, and notice the a values go on the upper left and upper right portions. A times c, which in this case would be 8 times negative 3, would go up top. And the b value goes on the bottom. We're going to talk about y1 and y2 in a second. So as you can see, we've got 8, we got negative 24 up top, and 2 on the bottom. Next, we have to figure out for y1 and y2 what values, when they multiply each other, equals that top value of negative 24, and when they add equals that bottom b value of 2. So again, you're just going to have to use your number skills and trial and error until you figure out that what would work is positive 6 and negative 4. 6 plus negative 4 is 2. 6 times negative 4 is negative 24. Next, we treat 8 over negative 4 and 8 over 6 like fractions, and we reduce them as follows, right? 8 over negative 4, you can divide the top and bottom by 4, so you get 2 over negative 1. Likewise, 8 over 6, you can divide both of those by 2, and you get 4 over 3. Those are the components of the factored form. So let me now show you how this next step works. So you take those values all color-coded, and we get the top value pairing up with the variable x and the bottom value as a standalone constant. So we have 2x minus 1 times 4x plus 3. And again, the order doesn't matter. It doesn't matter what goes on what side because multiplication is, of course, commutative. Then you look at each binomial separately and what makes each one go to 0. Well, for the one on the left, it's going to be 1/2, right? Because 1/2 times 2 is 1, minus 1 is 0. For the one on the right, what times 4 gives you negative 3? It's negative 3/4. And why do we want a negative 3? Because negative 3 plus 3 zeroes it out. So your two solutions are 1/2 and negative 3/4. Now we're going to talk about solving quadratics using completing the square. And by the way, this method is the least important of all the methods in the sense of you can either factor or you can also use the quadratic formula, which is golden and easier in a lot of cases for a lot of people. But I want to show you this method in case you like it, number one, and number two, because it will help you turn standard form into vertex form for quadratic functions. So let's say we take the same example, x squared minus 6x plus 8 equals 0. So then I'm going to space it out a little bit and I'm going to move the negative 8 to the other side. The reason why I leave this space here is because we're going to try and make a perfect trinomial that's a perfect square. So check this out. The way I do it is I take half of 6, actually half of negative 6, it doesn't matter. We'll just call it 6 because you're going to square it anyways. It's going to be positive regardless. So I'll just say half of 6, which is 3, and we're going to square it. So we add 3 squared, or 9, to both sides. So again, this is just the process that we follow. Then that turns into 9. And now on the left-hand side, I've got this perfect trinomial that now I can factor it to x minus 3 times x minus 3, which is the same as x minus 3 squared. And on the right-hand side, of course, negative 8 plus 9 gives us that 1. Now to solve, I can take the square root of both sides, right? Because the square root of x minus 3 squared is, of course, x minus 3. But the square root of 1, in this context, we have to remember, is both positive and negative 1. So you can see here we get two equations that we have to solve to give us our two solutions. Then in this case, we're going to add 3 to both sides, giving us x equals 2. And in this case, we're going to add 3 to both sides, giving us x equals 4. Those are your two solutions. Boom, done. Now we're going to talk about the quadratic formula, probably one of the most famous formulas in math. And the quadratic formula is as follows. So if we take a quadratic equation like this, 2x squared minus 4x minus 16. And again, they're color-coded. Red is A, blue is B, and green is C. You can see that x equals, again, because we're trying to find the x value that solves this, negative b plus or minus the square root of b squared minus 4ac all over 2a. So if you know this formula, it's pretty cool because it's always going to work and it's straight plug and chug. It's just kind of a little bit extra work sometimes if you can factor. That might be a little faster. But check it out. So I'm just plugging and chugging. All the blue values are now 4. All the red values are now 2. And of course, we got that negative 16 for C. And you can see that, remember, those minus signs, they stick to the values. So it's not just a 4, it's a negative 4. It's not just a 16, it's a negative 16. What's inside simplifies to 144, and then it's 4 plus or minus square root of 144 over 4. And again, the plus or minus is so you can get those two solutions, because now we have 4 plus or minus 12 over 8. So that means 4 plus 12 over 8 and 4 minus 12 over 8. And when you evaluate both of those, you get solutions of 4 and negative 2. Next, let's talk about exponential functions. So exponential functions in standard form are y equals a times b to the x power. Notice you have a variable for your exponent. A is your initial value. So think about a virus or a bacteria multiplying. And if you're trying to model the growth of that virus or that bacteria, that a value would be the starting population. Let's say you had 100 virus cells or 1,000 bacteria cells. A would equal that value. B is what we call the growth factor. So for example, if it's doubling every hour or tripling every hour, that B value would be 2 or 3. Or if it's growing by 50% every hour, that B value would be 1.5. So in this example here, we have y equals 3 times 2 to the x. So again, it would be doubling and with an initial value or starting population, let's say 3. And the graph of this would look like this. And notice that y-intercept is happening at 3. And it's not a coincidence that that's your initial value. And you can see here, if you plug in 1 for x, it's 3 times 2 to the first power, which is 6. And notice on the graph, we have 1, 6 right there. You can model two types of things with exponential functions. First, you can model exponential growth. That's what we just saw. That's like a virus strain growing, bacteria strain growing, etc. And this is where our b value is greater than 1. It's got to be greater than 1. Otherwise, it's going to be something called exponential decay. And if we talk about percentages, okay, let's say we have a growth rate of 5%. You don't put a 5 in there. You don't put a 0.05 in there. You have to add it to 1. That's what you do. So it's 1 plus that percentage growth rate change. So 1.05 would be your b value. Now, if we had an initial value of 10, the equation for this would look like this. Y equals 10 times 1.05 to the x. To show you the graph of this, it would look like this. We got that initial value or y-intercept right at 10, and then a more gentle slope, a more gradual build, because it's only going up by 5%. So again, we've got our y-intercept at the initial value of 0, 10, and it's a much more gentle slope than when the growth factor was 2, because it's only going up by 5%. And by the way, x can be any unit of time or whatever for modeling growth like this. It could be every week, every year, every month, depends on the setup. Now, when we talk about exponential decay, it's still the same baseline formula. It's just now that b is in between 0 and 1. So like 0.5, 0.4, etc. Now, if we talk about this in terms of percentages, if we have a 5% decay rate, meaning we're losing 5% every week, day, month, whatever it is. Again, you don't put in 0.05. So you do 1 minus the decay rate. So it's 1 minus 0.05, which would be 0.95. If it's a 10% decay rate, you'd put 0.9. a 40% decay rate, you'd put 0.6, etc. So here's what this function would look like. Again, an initial value of 10 and that decay rate of 5% represented by 0.95, and the graph would look like this. You see now it's going down as we go to the right. Again, we've got an initial value still at 0, 10 for the y-intercept. Now let's talk about radicals. Okay, a radical, the most common form is a square root. And we know square roots, right? Square root of 1 is 1, square root of 4 is 2, because what question are we asking when we take the square root of 4? What number times itself equals 4? And that's 2. And by the way, I'm specifically choosing perfect squares here, right? Square root of 9 is a nice 3, 16 is 4, 25 is 5, etc. And now if we talk about variables, right? The square root of x squared is x. Square root of x to the fourth is x squared. Why? Because think about exponent rules. X squared times x squared, you would add the exponents. Square root of x to the sixth is x to the third. Because once again, x to the third times x to the third, you'd add the exponent and you get x to the sixth. Then we've got these two additional examples just as a quick refresh. When we talk about cube roots, okay, we're talking about what number times itself again equals what's under that radical. So the cube root of 1, once again, is 1. But the cube root of 8 is 2, because 2 times 2 times 2 is 8. Cube root of 27 is 3 for the same reason. And once again, I'm picking perfect cubes. Cube root of 64 is 4. And cube root of 125 is 5. Again, if you want to check the math, what's 5 times 5 times 5? It's indeed 125. When we talk about from the variable perspective, the cube root of x cubed is just x, because x times x times x is x cubed. X to the sixth, that cube root is x squared. The other way to think about it, if you want a shortcut of taking a cube root, a fourth root, whatever, is you take the exponent inside, which is 6, and you divide it by that radical number of 3. So 6 divided by 3 is 2, 9 divided by 3 is 3, 12 divided by 3 is 4, and 15 divided by 3 is, of course, 5. Now let's talk about simplifying roots. And again, I want to look at this like a prison. That square root is a prison. I'm trying to get as many things out of that prison as possible. It'll still be part of the expression. But remember, the only thing that is able to come out, since it's a square root, are perfect squares. So check this out. I'm going to rewrite this as 2 times 16. Why? Because I know that 16 is a perfect square. So I'm just separating it out from a perfect square. I'm going to rewrite x cubed as x times x squared. Once again, x squared is a nice perfect square because the square root of x squared is x. Y to the sixth is a perfect square because it's got an even exponent. And then z to the ninth, I'm going to split it up as z and z to the eighth because once again, 8's an even exponent, we can take a square root. Now what I'm going to do is I'm going to take the square root of all of these perfect squares. So the square root of 16 is 4. So I'm going to throw a 4 on the outside. That is liberated. That can come out of the square root. Next, I'm going to take the square root of x squared, and that's just x, because once again, x times x is x squared. Then I'm going to take the square root of y to the sixth. That's y cubed, because y cubed times y cubed is y to the sixth. Last but not least, I'm going to take the square root of z to the eighth, and that is z to the fourth, because z to the fourth times z to the fourth is, of course, z to the eighth. Right? Just as a refresh, we're adding those exponents. What about everything else? Those are all stuck inside of the square root prison. The 2, the x, and the z have to stay back. Boom, done. Now let's talk about solving equations that involve radicals. So for example, we got x plus 1 under square root equals x minus 5. Once again, it's a prison. In order to solve, we must liberate the left side. Well, how do we get rid of the square root? We can do the opposite, the inverse operation of square rooting, which is squaring. So I'm going to square both sides, which is pretty cool. Because on the left side, the square root just is destroyed. Now it's x plus 1. On the right side, we get x squared minus 10x plus 25. Why is that? Again, because don't just think about squaring each individual component. We're foiling, right? We're taking x minus 5 times x minus 5, and then you're foiling, and you get that x squared minus 10x plus 25. Just to show you what it looks like, I'm going to write it out for you. So you have x minus 5 times x minus 5, and you would go like this. X times x is x squared. X times negative 5 is negative 5x. Negative 5 times x is negative 5x. And then negative 5 times negative 5 is 25. These guys are like terms, and they combine to be negative 10x. And hence, you get the x squared minus 10x plus 25. Then I'm going to move the x and the 1 on the left side to the right side because we want to follow that zero product rule. So when I subtract 1 from both sides, I get 25 minus 1, which is 24. When I subtract x from both sides, I get negative 10x and negative x, which makes negative 11x. Next, I'm going to factor. And once again, we're asking the question, what multiplies to 24 and adds to negative 11? That would be negative 3 and negative 8. And since we can once again use our zero product rule, we know that the solutions to this are both 3 and 8. But we're not done yet. When it comes to these types of functions, we need to check. And what do I mean? I mean, we need to plug them back into the original equation and make sure everything works. The thing you want to be mindful of is we're only taking positive square roots in these types of situations, in these types of equations. Let me show you what I mean. So first, if I plug in 3, I get 3 plus 1 equals 3 minus 5. Square root of 3 plus 1 is square root of 4. And on the right, we get negative 2. Now, you might be saying, well, wait a minute. Square root of 4 can be both positive and negative 2. But again, in this situation, we're only looking at the positive square root. So this, in fact, gives us 2 equals negative 2, which is obviously not correct, which means that 3 is not a viable solution. Now we have to check with 8. So underneath, we get 8 plus 1. On the right, we get 8 minus 5. This leads us to the square root of 9 equals 3. Well, guess what? The square root of 9 is positive 3. 3 equals 3. Therefore, 8 is indeed verified as a solution. Now let's talk about when we have radicals in the denominator and what we have to do. We have to rationalize the denominator. A lot of questions will just say simplify. They won't tell you this, but if there's a radical in the denominator, that's what they expect you to do. So check it out. Let's say we have 3 over square root of 5, and we need to rationalize the denominator. We need to turn that square root of 5 into a rational number. The easiest way to do that is to multiply the top and bottom by square root of 5. Okay, why does that help? Because any square root times itself is just the number. You're liberating it. So square root of 5 times square root of 5 is 5. And on the top, you got 3 square root 5, and that's okay. You can have an irrational number on the numerator, so this is good to go. This is fully simplified. If we take a more complicated example of 3 over 4 plus square root of 5, we can't just multiply by square root of 5 because we'll still get a radical in the denominator. Here we have to use something called a conjugate, so check this out. I multiply by the same thing I got in the denominator, but I switch that plus to a minus. Now, if it were a minus, I switch it to a plus. So it goes like this. 4 minus radical 5. But I have to do the top and bottom as the same, obviously, because it has to equal 1. So now I multiply across, and I get on top 3 times 4, which is 12, minus 3 times radical 5, and that's it. On the bottom, I get 16 minus 5. No radicals. Why is that? Let me show you. So again, it's another foiling situation. I get 4 plus square root of 5 times 4 minus square root of 5. And if I FOIL, boom, I get 16. And then boom, minus 4 rad 5. Boom, plus 4 rad 5. And then boom, rad 5 times rad 5 is 5, but with that minus is minus 5. And then look, these guys are opposites. They cancel out. That's what we want. And that's why we end up with 16 minus 5. So now we can simplify this to 12 minus 3 radical 5 over 11. Boom, done. Next, let's talk about rational exponents. So these are essentially exponents that are fractions, and we want to convert them to radical form a lot of times to evaluate them. So check this out. Let's say we have 8 to the 2/3 power. So it's important to know what each component of that fraction means. For example, the numerator, the 2 is actually the power. It's like 8 to the 2nd power, and that 3 is the root. So that means the cubic root. So we're simultaneously squaring and then taking a cubic root of this number. So for example, I could write it like this, 8 squared, and then the cube root of that result. I could also write it like this, the cubic root of 8, and then take that and square it. Now, I often prefer this second way because it's easier. We're going down first. We're going down to 2, that's the cubic root of 8, and then squaring that, versus going all the way up to 64 and then finding the cubic root. So we can see that if we use the first method, we square it, we get 64, cube root of that is 4. And then the second way, we take the cube root of 8, which is 2, and then square that, and we still arrive at 4. Now, when we talk about exponent rules, we need to know what happens when we multiply and divide with the same base. That's the key. So now let's say we have x to the 7th times x to the 4th. When the bases are multiplying, we add the exponent. So you add 7 plus 4 and you get x to the 11th. Conversely, when we're dividing with the same base, let's take the same example, x to the 7th, but now we're dividing by x to the 4th, we subtract the exponent. So we take 7 minus 4 and we get a result of x to the 3rd power. Now let's talk about simplifying multiplying rational expression. So we're going to take this example here. And again, a rational expression, it's just a polynomial divided by another polynomial like this. And we're going to take a complicated one where it's this whole expression divided by this expression. So the first thing you want to do is we want to change that division to a multiplication, because then we can actually simplify much more easily. So we remember our keep, change, meaning we change the division to a multiply, and then flip. It's the same thing that we learned back in the day when dividing fractions. Here, it's the same thing with these rational expressions. So keep, change, flip. Next, we want to factor, factor, factor. So you notice up top, we were able to factor 3x squared minus 2x minus 5 into 3x minus 5 and x plus 1. On the bottom, we were able to factor out a GCF of x. And now on the right side, in that 9 minus 15x, we can factor out a 3. That's again a GCF. Now, once we have it all laid out like this, we can cross off terms that appear both on the top and the bottom. And we're able to do that because everything is multiplying everything. If there were any separations of the terms with pluses or minuses, we wouldn't be able to do this. So I can cross off the 3x minus 5 on the top and the bottom, and the x plus 1, and there's an x on top, x on bottom. And last but not least, that 3 on top and the 3 on bottom cancel out as well. And guess what? Everything kind of cancels out beautifully, and this reduces to 1. Next, we're going to talk about polynomials. Okay, so what are polynomials? Polynomials are just these nice expressions with variables and numbers. So check it out. We got this guy, x cubed plus 2x. By the way, this is a cubic polynomial because the highest degree is a cube, and we call it a binomial because there are two terms. Not that you need to know these terms, but I'm just giving you context. This is a quadratic trinomial. It's quadratic because the highest degree is 2, and it's a trinomial because, of course, we have 3 terms. Here, the highest degree is 5, and of course, we have 5 terms as well. We talk about a monomial. A monomial is a type of polynomial, but it's just one term. So here we have 3x to the 6th. It's the 6th degree, but it's just one term all scrunched together. So that is a monomial. Now we're going to talk about operations with polynomials where we can add and subtract them. So check it out. We're going to take this example of 3x squared minus 2x minus 5 plus 4x squared plus x plus 2. Again, it's all about adding and combining like terms, and the exponents change it. So for example, the x squareds are like terms with each other, and the x's are like terms with each other, but the x squareds and the x's in this context don't mix. So for example, check this out. First, I'm going to move all the parentheses because they're not really doing anything. We would try to maybe distribute a negative if need be, but that's not needed here. So now check this out. These guys match up, we're going to combine those. These guys match up, and we're going to combine those. And of course, the constants match up, and we're going to combine those. But don't forget that minus with the 5 actually sticks to the 5. That minus with the 2x actually sticks to the 2x. So that's a negative 2x and a negative 5. So 3x squared plus 4x squared is, of course, 7x squared. Negative 2x plus x is negative x, and negative 5 plus 2 is negative 3. Boom, done. Now let's take the same example, but we're subtracting them. Now we have a minus in front of the second polynomial. This is a different scenario because now we have to distribute that minus to every term on the right. So check this out. The left term stays the same, but the right term now it's minus 4x squared, minus x, minus 2. So once again, we're going to combine those guys, the x squareds, and it's a negative 4x squared now. We're going to combine the x's, and they're both negative, and then the constants, which again are both negative as well. So 3x squared minus 4x squared is negative x squared. Now, I could say negative x squared or negative 1x squared, just to remind you that there's always an invisible 1 next to any variable that is just sitting there without a coefficient. Likewise, in that first example, 7x squared minus x, that's really a minus 1x. With a negative 2x and negative x, that gives us a negative 3x, and then of course the negative 5 and the negative 2 gives us negative 7. Now let's talk about multiplying two polynomials, and this is going to be an expansion of the typical foiling that we see because this is going to be a binomial times a trinomial. So check it out. We're going to jump over, and every term in the first binomial is going to hit every term in the second trinomial. First, we have 2x times 4x squared, which gives us 8x cubed. Then we have 2x times x, which gives us 2x squared. Then we have 2x times 2, which gives us 4x. Then we hit the negative 5 up and multiply down the line the same way. So then we have negative 5 times 4x squared, which is negative 20x squared. Negative 5 times x, negative 5x, and of course negative 5 times 2, which is negative 10. Now we're going to combine like terms. You can see that the 2x squared and the negative 20x squared are going to make a negative 18x squared. And then that 4x and negative 5x are going to make a negative x to give us this final polynomial. Now let's talk about synthetic division when we're dividing two polynomials. So this is a really nice trick if you do indeed need to carry this out on the ACT. So let's say we have 1x cubed plus 4x squared minus 3x plus 1 divided by x minus 1. Now, of course, you can do long division, which I'm going to get to in a second. But in something like this, where we're dividing by this nice simple binomial of x minus something or x plus something, you can use synthetic division and it's a lot faster. So check this out. First step, I'm going to take all the coefficients of that first polynomial, 1, 4, -3, and 1, and I'm going to place them like so. Then I'm going to take that orange number, the 1, what x is subtracting, and I'm going to throw it in a little box like this. Now again, if it was x plus 1, a -1 would go in that box. Now here's the process. We drop that first 1, then it multiplies what's in that box, and then we throw it here. And then we add straight down. 4 plus 1 is 5. Next, repeat. 5 times what's in the box. 5 times 1. Drop it here. That's a 5 there. Add straight down. -3 plus 5 is 2. Boom. Next. Then we multiply again to what's in that box. 2 times 1. Drop it here, which is 2. Add straight down. 3, and that's my remainder. So now you're wondering, what does this tell us? This gives us the resulting polynomial when we divide. And again, it started at x cubed, so now this first term is one level down at x squared. So check it out, it's 1x squared, c plus 5x plus 2, and then that remainder plus 3, and that remainder goes on top of the original divisor. Now let's talk about long division, and long division is really important when you see in our second binomial, it's no longer just an x minus 1 or x plus 1, there's a coefficient in front of it, and this is where long division comes in handy. So long division is just like the long division we learned back in the day, so check it out. We're going to set it up just like this, divisor on the outside, boom. All we're looking at is that leading term. For example, we're looking at the 2x and we're looking at the 4x cubed. I'm kind of ignoring everything else. So my question first is, what times 2x gives me 4x cubed? Well, that's going to be 2x squared, right? Because then I multiply it and I get 4x cubed. But I also have to multiply the second term. So what's 2x squared times -1? -2x squared. Now, just like in regular long division, we need to subtract the bottom part from the top part. So what I like to do is I go negate, negate. It's like I'm distributing the negative or the minus to both of those terms. And then I just straight up add. 4x cubed plus -4x cubed cancels out. Boom, that's what we want. And 4x squared plus 2x squared gives me 6x squared. Now we drop the next term of -8x and we continue. Again, focusing only on 6x squared. So what times 2x gives me 6x squared? That would be 3x, a positive one. Now I'm going to multiply it. 3x times 2x again is 6x squared, and 3x times -1 is -3x. Now we repeat that step before. Check it out, negate, negate, and now we just straight up add. Those two cancel out, and -8x plus 3x is -5x. Once again, we drop that 1 and do it one more time. What times 2x gives me -5x? That's -5 over 2. And boom, we get a -5x, and then -5 over 2 times -1 is +5 over 2. Again, negate, negate, combine. Those guys cancel out. 1 plus -5 halves is, of course, -3 halves. And that's my remainder. And so we end up with the final polynomial of what's on top, 2x squared plus 3x minus 5 halves. And then plus that remainder, which is negative. So now it's a minus 3 halves over 2x minus 1. I just dropped the 2, the denominator, boom, done. Now let's talk about polynomials and factoring. So check this out. When we've got an x squared plus 2x, you want to know how to factor this. This is more about a GCF, right? So what's common to both terms in x, right? So what we can do is we can yank that x on the outside, and what's left inside? X plus 2. And we know that's true because if you redistributed the x, you'd get x squared plus 2x. Factoring is super important on this test, and a lot of times when they want you to simplify or do different things like that, you're going to have to just simply almost blindly factor and see what happens. When it comes to factoring a trinomial like this, remember it's likely going to factor into two binomials if it indeed is factorable. So check it out. This becomes x plus 2 times x plus 5. So why does that work? So if we remember about foiling, kind of like we did in that previous example, remember to redistribute, it would go x times x, which is x squared, and then x times 5, which is 5x, and then 2 times x, which is 2x, and then 2 times 5, which is 10. So you see when we combine the like terms in the middle, we come back to our original polynomial. So that's how you want to think about factoring. And you can see that, of course, if we have an x squared here, we need an x and an x in that first spot. And then what goes here and here is going to multiply to 10 and add to 7. Next, we have 4x cubed minus 21x squared plus 29x minus 6. And not like they're going to give you something this complex to actually straight up factor, but for example, this does indeed factor to this set of 3 binomials. Now we're going to talk about how the factored form helps us find zeros, and that's really important on the ACT. So for example, if we had this as a function and then we factored it as x times x plus 2, we can easily find the zeros. And when I say zeros, it means the values of x that zero out the function to give a function value of 0. Well, guess what? For this x, if I just plug in a 0 here, 0 times anything is 0. What about in this binomial? If I plug in a -2, it zeroes out. So my two zeros are therefore 0 and -2. In this example, once we factor it into x plus 2 times x plus 5, my zeros are what makes this go to 0, which is of course -2. -2 plus 2 is 0. And here -5. -5 plus 5 is 0. Those are the winners. Boom, done. Finally, with this big dog, when we factor it up, check it out. It's the same simple process despite it being a much bigger polynomial to start with. So this section, 3 would zero it out, 2 would zero it out, and here it's a little trickier, but it's 1/4. So my 3 zeros are as follows: 1/4, 2, and 3. Now we're going to quickly talk about sum and difference of cubes. This isn't on the ACT a whole bunch. It's probably pretty rare, but I'm going to throw it on here just in case if you do want to put it in the memory banks just to be extra prepared. So check this out. We have a sum of cubes first, okay? This is x cubed plus b cubed. The way I like to remember this is this following little handy thing, which is same, different, plus. Okay, so what do I mean? When we factor it out, okay, we have the same sign as there, then we have the different sign. So if it's plus, now it's minus, and then the last one is always plus. You'll see this come in handy when we do difference of cubes because it's the exact same thing, same, different, plus. And generally, this is how it foils, right? We have whatever to the third power here and whatever to the third power here. That x value is going to go here, and that single b value is going to go there. Then we have x squared minus the product of x and b, again, the cube root of these original terms, plus b squared. Now for an example, we have 8 plus y cubed. Again, 8 is 2 cubed. So the cubic root of 8 is 2, that goes here. Cubic root of y cubed, that goes here. And then of course, this is 2 squared minus 2 times y right here, and then plus y squared, which is like the b squared up top. Now for a difference of cubes, x cubed minus b cubed, it's again same, different, and plus. And to see an example, we have 64 minus 27y cubed. So again, those are both perfect cubes. The cube root of 64 is, of course, 4. And the cube root of 27y cubed is 3y. 3 times 3 times 3 is 27. Y times y times y is y cubed. So again, we have same right here, minus, minus, different because it's a plus and that's a minus, and then plus, right? And again, here we have 4 squared. Here we have 4 times 3y, again, multiplying these two terms. And then here we have the b squared, which is 3y squared, which is the whole thing, 3y to the second power, which gives us 9y squared. Now, just to put it all together, if we want to see the zeros, by the way, of those polynomials we were talking about previously, check this out. Here's a graph of these polynomials. So let's look at this really complicated one that we factored like so. What is that going to look like on a graph? We already said the zeros were 1/4, 2, and 3. So if we look at it on a graph, check this out. It's hitting the x-axis. Those are the zeros where the function value is 0. It's hitting the x-axis at 1/4, 0, at 2, 0, and of course at 3, 0. Now let's talk about linear and quadratic systems. Of course, they're going to be linear systems, but what about linear and quadratic? The same thing. It's like, where's the line intersecting the parabola? Let's take the example of y equals x squared minus 6x plus 3 for our quadratic, and y equals negative 2x plus 3 for our line. So if we were to look at the graph of this, we can see that it intersects at 2 spots, right? It intersects at 0, 3, and also at 4, -5. So if you're trying to solve this system, those would be your solutions. By the way, that you could also solve this algebraically as follows, using a little substitution, right? I can set these guys equal to each other. Negative 2x plus 3 equals x squared minus 6x plus 3. And then check this out. These guys cancel out, right? You have the same thing on both sides. They just nix them by subtracting 3 from both sides. And then I'm going to add 2x to both sides. And why are we doing this? Because we want 0 on one of the sides, 0 product rule. So now we have 0 equals x squared minus 6x, negative 6x plus 2x is negative 4x. And there's no more constant. So now this is pretty easy to factor because all we got to do is pull out a GCF of x. And what's left aside is x minus 4. Guess what? We got 2 solutions. To 0 this out here, we just need x to equal 0. And to 0 this out, we just need x to equal 4. And those are the 2 solutions. And that's what we see here and here. Now, if we wanted to get the corresponding y values, you just plug them into either equation. Let's plug them into the bottom because it's easier. 0 times negative 2 is 0 plus 3 is 3. So we have 0, 3 as one solution, just like we see here. Plug 4 in. 4 times negative 2 is negative 8 plus 3 is negative 5. Boom, done. Now let's talk about function notation. So this is an interesting way to present these functions. A lot of us are used to originally seeing it as y equals 3x plus 7. And then we just swap out the y for f of x. So now it's f of x equals 3x plus 7. But the same thing, just like g of x equals 5x. Same thing as y. So these are just 3 different functions. And now I'm going to show you what function notation means in this context. So let's say we had f of 3. A lot of times people think, oh, that means f times 3. No. I've replaced the x with a 3. So in the actual function, I'm going to do the same thing. I'm going to replace x with 3 and solve for the function value. Check this out. So now I've got 3 times 3. Again, the x is replaced with 3 plus 7. That's 9 plus 7, which gives us a function value of 16. Next, let's look at g of 0. So again, we're plugging in 0 for x. So this would be 5 times 0, which of course is 0 for the win. Last but not least, let's take h of negative 2. So I'm going to plug in negative 2 for x, so negative 2 squared plus 3. Negative 2 squared is of course positive 4 plus 3, which gives us 7 for the win. Done. Now, once again, taking the same 3 functions, let's look at some other function operations. So what if it said f of 1 plus g of 3? It's the same deal. We have to calculate f of 1 and g of 3 and add them together. So it'll be like f of 1 is 3 times 1 plus 7. G of 3 is 5 times 3. And then we just got to add them together. So 3 plus 7 is 10, plus 5 times 3 is 15, which gives us 25. Boom, done. So what does g times h of negative 1 mean? It means we're taking g of negative 1 times h of negative 1. So what's g of negative 1? Plug negative 1 in for x, and 5 times negative 1. What's h of negative 1? Plug that in for x squared. So then it's negative 1 squared plus 3 like this. So that's negative 5 times 1 plus 3, which is 4, which equals negative 20. Last but not least, h of g of negative 2. So you notice now this is an open circle. That's different. So check this out. This actually means h of g of negative 2. So it's like we find what g of negative 2 is, and then we plug that into h. So let's go here. What's g of negative 2? G of negative 2 is 5 times negative 2, right? In that g function, I plop it in. 5 times negative 2 is negative 10. So then what am I really taking? Since I know g of negative 2 is negative 10, I'm really taking h of negative 10. So now I plug negative 10 in for h. So it's negative 10 squared plus 3. That's 100 plus 3, 103. Boom, done. Now let's talk about logarithms. So there's not a crazy amount of logs on the ACT, but you do need to know the basic rules to be able to handle all these questions. So I'm going to break it down as simply as possible. So first of all, log of base A of B equals C. This can be translated to an exponential expression. This is probably the most important thing that you need to know about logarithms, because a lot of questions just want you to translate into exponential and solve. So check this out. This is the same as saying A to the C power equals B. So if you can do that simple conversion, you can solve a lot of the log problems on the ACT. So for example, log base 2 of 8 equals 3. Yes, that's true because it means 2 to the third power is 8, which we know is absolutely true. So now if we take an example where we're actually trying to solve, let's take log base 3 of 81 equals x. We're like, what is x? Well, this can be rewritten as 3 to the x equals 81. Well, 3 to what power is 81? That's 4, right? Because 3 times 3 is 9, times 3 is 27, times 3 is 81. So x equals 4 for the win, done. Now here's some other rules that are tested on the ACT, but I'd say, again, conversion to exponential form is the most important thing. But let's check these out. So for example, if I have log base a of x plus log base a of y, and again, those bases got to be the same, I can rewrite this as log base a of x times y. We can condense those. If it's subtraction, we can rewrite it as x divided by y. So it's very interesting. So this is just some of the rules that are often tested on the ACT. We can kind of condense those as well. Another rule is if we have an exponent on top of that x value, it is the same thing as if we bring it down in front of the log. So log base a of x to the b is the same as b times log base a of x. And another simple thing, log base a of 1. Log base anything of 1 is always 0. Why is that? Because this is the same as saying a to the 0th power is 1. Well, anything to the 0th power is 1, so that makes sense. And last but not least, log base a of a is 1. Why does that make sense? Because what is this really saying? A to the first power is, of course, itself. It's a. Now we're just going to go through some concrete examples of seeing these rules in action. So for example, log base a of x plus log base a of y equals log base a of the product of the two. This means log base 3 of 2, log base 3 of 5. If you add them together, I can multiply the 2 and the 5, and it's the same as log base 3 of 10. Here's a subtraction one where we're talking about division. So doesn't this make sense, right? Log base 6 of 30. And again, the bases have to be the same to do this. Minus log base 6 of 5. Well, it's the same as 30 divided by 5, meaning log base 6 of 6. On a side note, log base 6 of 6 is, of course, 1, but again, that's just a side note. Log base a of x to the b. Remember, we can drop that b down. So check this out. If I have log base 2 x to the 7th, it's the same as dropping that 7 to the front. Likewise, in this simple rule, log base 9 of 9 is again going to equal 1, right? Any base, like we said up top, log base 6 of 6, 1 as well. Now let's talk about matrices. So matrices, what is a matrix? It's like rows and columns and a set of numbers. We use these in computer science and all sorts of things, but really all you want to know for the purposes of the ACT is it's just rows and columns of numbers. This one here is a 2 by 3 matrix, meaning it has 2 rows and 3 columns. This one down here is a 2 by 1. Again, it's got 2 rows, right, the top and bottom, and only 1 column. So first, let's talk about scalar multiplication. You're going to have to know how to do this, and it's really not that bad. So let's say we have 3 as our scalar. That means just a number that we're going to multiply by. And we got a matrix here, right? This is a 2 by 2, and it's 3, 5, 8, 2. How do we multiply? Well, simply distribute. That 3, that scalar multiplies every value in the matrix. So check it out. First, we got 3 times 3, 3 times 5, 3 times 8, and 3 times 2. Everything retains its original position. And that gives us a new matrix, a new 2 by 2 of 9, 15, 24, and 6. Next, let's talk about matrix addition. Once again, it's fairly straightforward because when we add two matrices, first of all, they have to have the same dimensions, which they do here. But all the positions, like the upper left, the bottom right, they just add together to each other. So check this out. I have 3 plus 1 in that upper left-hand corner. Then over here, I add the 5 and the 7 in the upper right-hand corner. Then I add the 6 and the 8 in the bottom left, and that stays in the left. And then we add the 2 and the 4 on the bottom right. Now, as we complete the addition, we end up with 4, 12, 14, and 6 for the final answer. Now, by the way, you could also have matrix subtraction. It's the same idea as the addition. Instead, you're just subtracting all the terms, right? If I had a subtraction there instead of addition, it'd be 3 minus 1 instead of 3 plus 1. Now we get to the most difficult concept for matrices, which is matrix multiplication. So this, you just might have to watch this part a couple times, but here's the process. Now, firstly, in order for matrix multiplication to even happen, the first one has to have the same number of columns as the number of rows for the second one. That might not make sense yet, but just hang with me. And by the way, they test this exact rule many times without even showing you the matrices. They just say, hey, here's the number of columns for A, here's the number of rows for B. Which one of these cannot multiply? And of course, check this out. The number of columns, which is 3, does happen to equal the number of rows, which is also 3. So now how does this multiply? We'll check it out. First, we kind of do this interesting distributive process. The 5 comes here and hits that 5, plus 7 multiplying this one down, plus 8 multiplying this one down. So you see the columns shoot across as we go down in the rows. So in this first position in the upper left, we get 5 times 5 plus 7 times 2 plus 8 times 4. And just as a side note, see how the number of columns equals the number of rows? For the final matrix, it will have the number of rows of the first one, which is 2 rows, and the number of columns of the second one, which is also 2. So you'll see this ends up being a 2 by 2 matrix. Okay, now what about the next spot over up here? What's going to go there? So check it out. We're going to continue that same process, but now we go 5 times 7 plus 7 times 3 plus 8 times 6. So you can see it kind of keeps going across and down, across and down. So check it out. We've got, boom, 5 times 7 plus 7 times 3 plus 8 times 6. Now we get to the bottom, guys, the purple numbers. So again, it's a similar process. We go 2 times 5 plus 3 times 2 plus 9 times 4. Check it out. Boom, there it is. And last but not least, we're going to go 2 times 7 plus 3 times 3 plus 9 times 6. And that's going to go in the bottom right-hand corner. So now once we carry out all that arithmetic, we end up with a final 2 by 2 matrix of 71, 104, 52, and 77. Boom, done. The final topic we're going to cover in this video are vectors. And vectors can definitely be confusing, but they're not tested to that great of a degree on the ACT, which is good news for you. So check it out. What is a vector? A vector sort of describes both magnitude and direction. But again, you don't even really need to know all of that. So check this out. This is kind of your general format of a vector, 3i plus 4j. So what's the I? What's the j? The I kind of describes horizontal movement and the j sort of vertical. And by the way, we should also be familiar with its component form where you just take those two values, the numerical values, you can say 3, 4. So what does this mean in terms of what this vector looks like? Well, check it out. It means it goes 3 across, 3 to the right, because again, it's positive. If we're negative, it'd be going left, and then 4 up. So the final vector looks like this diagonal line, which is pretty cool. So again, that has a representation of direction, meaning kind of like the angle it's going at, plus the magnitude, which is really the length. And by the way, we can now calculate the magnitude of this vector. And doesn't this look like a right triangle? So guess what? You would use Pythagorean's theorem to get a magnitude, which is 5. And how do we do that? How do we calculate that magnitude of 5? Check it out. We do our Pythagorean's theorem. 3 squared plus 4 squared equals c squared. Again, it's that length of almost like the hypotenuse of a right triangle. So that gives us 9 plus 16 equals c squared. 25 equals c squared, which then means that c equals 5, which is the square root of 25. And that is our magnitude done. Now let's talk about some of the operations you might have to do. You could have vector addition. So what does that look like? Well, let's first take these two vectors in their component form. We got 5, 1 plus 7, 4. So first, what does this look like when we're just straight up finding the answer? You add the two initial parts, the horizontal changes to each other, and you add the vertical changes, 1 plus 4, and you get a new component vector of 12, 5. So what does this look like if we're actually adding vectors? Check this out. So first, we have our 5 in the original purple vector, going 5 across and 1 up. There's our purple vector, right? And then what about our green vector? And by the way, when we add vectors, we go head to tail, head to tail. So check this out. I'm going to start with the new vector right where that head of the purple vector ends off. So we go, boom, across 7, right? That's the 7i. And then we go up 4j. So we're going up 4, and there's my green vector. And then my final vector is from the starting point of the original vector, the purple vector, all the way up to the tip of the green. So that's the big dog. And so how do we find the magnitude of this final vector? Well, again, I've got the 12 left and 5 up, right, in the final component vector. So we use Pythagorean's theorem once again. 12 squared plus 5 squared equals c squared. So that's 144 plus 25 equals c squared. That gives me 169 equals c squared. Well, what's the square root of 169? That is 13 for the magnitude. Boom, done. Now let's talk about vector subtraction. It's not much different than vector addition. So check this out. Let's say we're subtracting these two component vectors. So as common sense might dictate, we're just subtracting each piece. So it's 6 minus 3, 7 minus 3, and that gives us a new final component vector of 3, 4. So what does vector subtraction look like? All right, so check this out. Once again, we're starting with the purple one. We're going across 6 and up 7. And of course, there's the purple vector in this case. So now how do we approach the minus? It's almost like I'm negating the 3 of each 3 in that green vector. So instead of going right by 3, now I'm going left by 3. Instead of going up by 3, I'm going down by 3. And so there's the new vector, and there's the ending point. So you see, once again, we're still going head to tail like that. And then the final vector, the resultant vector, is this black one, right? So we're starting again at the beginning of the first vector, and we're ending at the head of the second vector. And we can now calculate that magnitude. And since we know the final component vector is 3, 4, we use 3 squared plus 4 squared equals c squared. That's 9 plus 16. Once again, 25. Square root of 25 is 5. So that gives us a magnitude of 5. Boom, done. Last but not least, let's talk about scalar multiplication with vectors. So what if I had a vector u and I have another vector v, right? So we got 6, 7, 3, 4 in component form. Now, what if the question asks, what is 2u plus 5v? So again, it's kind of based on common sense, because you could almost treat this as like coordinates or similar to a matrix. You're just distributing the 2 to each. You're distributing the 5 to each piece. So what does that look like? So the new first one is going to be 2 times each of the components of u, right? 2 times 6, 2 times 7. And then for the v, it's going to be, since there's a 5 in front, it's going to be 5 times each of those pieces. 5 times 3, 5 times 4. So now we have 12, 14, 15, 20. And just like with the addition before, we add the like parts. So we get the 12 plus 15, as those are the first pieces of these vectors, and then add the 14 and 20, which gives us a final component vector of 27, 34. That's it for this series on advanced mathematics for the ACT. Make sure to check out parts 3 and 4 to get a comprehensive view of all the math concepts you need for success on the ACT. I hope you enjoyed this video, and if you did, please click that like button. And if you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.